Alright, so good evening and welcome to the stream again. I am currently at the OCaml retreat in Auroville, which is near Pondicherry in Tamil Nadu, India. So been here for this week, and I am on a low speed internet connection. I didn't do streaming on Monday, and there was some background noise, so I have done some post processing on the video, and I have uploaded on the YouTube site here, so you should be able to go and check the basic data types and pattern matching part 1. We will try and finish this section of the documentation today. Before we actually start with the hands-on work, a couple of announcements. So Thibaut has recently announced on starting a OCaml meetup in Manila, Philippines. So this is the relevant tweet. If you can retweet it and make people aware of it, it would be quite useful. There is a meetup.com page with information. So this is scheduled to start on Thursday, April 4th. Right, this is at a cafe. Let me paste the relevant URLs on the chat. Okay, this is the tweet, and this is the link to the meetup. Sabine has also created a OCaml.org Twitter account. It's actually OCaml_org to be specific. So feel free to follow for updates on this account as well. So with that, let's get started for today's session. So we have been going through the OCaml.org documentation, and to be specific, we have been going through the basic data types and pattern matching section. So we covered the basic types. Now we're looking at user defined types. So let's continue this section. So we use the type keyword for defining user defined types. We can have variants or records or aliases. Now let's take an example of enumerated data types. So this is an example of a user defined data type which represents the Dungeons and Dragons characters. Let's quickly try this in the OCaml play environment. I'm just going to clear the output here. So we use the type keyword, and then we define character class as, say, barbarian or bard, cleric, druid, fighter, monk, paladin, ranger, rogue, sorcerer, or wizard. Right, let's run this, make sure the definition is correct. It looks good. And then of course we can further define rectitude as evil or neutral or good. I'm intentionally typing this because when you revise and review these sections, I would like you to have the browser and also the OCaml.org play site and manually type it so that you understand the syntax. Avoid copy pasting as much as possible. So then we have firmness is chaotic, F neutral or lawful. Right. Let's clear the output and run it again, and there are no errors. Okay, that looks good. So another example would be to define our weekdays and weekends, right? So let's try defining weekday. For example, let me clear the output here. So we use the type keyword. I can say weekday is, let's say, starting with Monday or Tuesday or Wednesday or Thursday or Friday, and close with double semicolon. We run it, that's fine. So similarly we can define a weekend to be a Saturday or Sunday. So these are constructors, right? So both definitions are good. One important thing to remember is there is ordering here. So if I check for, say, is Monday is less than Tuesday, this should return true, right? That's the condition here. But if I did something like is Thursday less than Wednesday, which is not, and I run it, it will return me false, right? So this ordering exists when you define these constructors. Of course, we can have constructors with data. So let's take an example here for a commit message. So we can define this as, let me clear this, clear the output as well. So we can define a commit as a hash of string, right? Or it can be a tag of string, or it can be a branch of string, or it can be a head, it can be a fetch head, origin head, or it can be a merge head, right? So the definition looks fine. So how would I use it? So if I want to create an instance value for this, I would say something like hash of, say, 991 F67, for example. So let's say hash of string. So that's an example of a commit type. Now we can of course do pattern matching on these user defined types. So let's try to define these two functions, commit to string. So first one uses the function construct. So I can define this as let commit to string. It's a function. So if I have hash of SHA returns SHA, or you have tag name, just return the name. And these are simple examples, but they are easy to follow and help you understand the usage. So if it's a head, I just return a head string, and if it's fetch head, again I'm returning a fetch head string, and if it's orig head, I return orig underscore head as a string, and then for merge head, I return merge head. Close it with the double semicolon. Let me run this again. Okay, that looks fine. Of course, OCaml, we would like to use the match with construct. So we can of course rewrite this as commit to string, the new definition of x, you match x with can say hash return SHA, and tag name should just return name, and we have branch name should return name, head should return head, and fetch head should return in capital letters fetch underscore head. Orig head should return orig head, and finally merge head should return merge head. Okay, let's clear the output. Let's run it again. Okay, that looks fine. Right. So the function construct is a special form of a anonymous function, but really match is the construct is used often. So an important point here to remember is when you have like product types, right? They are considered to be a single parameter. So let's take an example here when we are doing user defined types. So let's define a type T which has C1 constructor which is of type int bool, so that's, and C2 of int bool in parenthesis. So C1 has two parameters, C2 is considered to be a single parameter, right? So to illustrate this concept, let's say P is equal to 4 comma false, it's a tuple. Let's quickly run this to make sure so it's fine, it looks good. So if I do like C1 of P, right, it basically will throw an error saying constructor C1 expects two arguments, which is int and bool, right? So it doesn't satisfy that. But if I do C2 of P, right, it should basically accept it. So it's very important to remember that when you use parenthesis in this user defined type definition, it represents a single parameter. Moving along, we can define recursive variance, a definition that is referring to itself is recursive. So in this example, we are defining a JSON type. So let's do that. Type JSON is either null, it has a bool, it can be an int of int, float of float, can be a string, or it can be an array of JSON list, right? So this is a recursive definition. And similarly, object of string and JSON, which is a list, right? So the array and object both contain values of JSON. So it is an example of a recursive definition. We can again do pattern matching with functions operating on recursive variance, and when we do that, we would usually use the rec keyword because of the recursive nature. So the function will also be recursive in nature. So let's try this example here. So let rec has field name. So if it's an array, so we define the JSON type, and the two cases of array and object we saw the recursive definition, right? So here I'm just going to call, don't worry about the fold dot left. When we go through the list module, I will explain what it represents. So we are passing a function b object b or has field name obj false u, okay, or in the case of an object we again call list dot fold left, the function j returns b, or key is equal to name, or has field name obj, false u. If there's anything else, I just return false. So don't worry too much about the actual use of list.fold left. Definition looks fine. What I want you to remember here is, for this recursive definition of has field, we use the rec keyword, and we're again calling has field in each of these cases. Okay. Right. The next section is on polymorphic data types. So we have seen the option type. So if we do show option, for example, it can be none, or it can be sum of type A. So A can be integer, or it can be a string. So it can be sum 42 or sum hello. So this we say is a polymorphic type. Another example is, of course, show list. We have seen examples of integer list or string list or boolean list, right? So that's the definition. The bool and unit are regular variants as described in this documentation. So I can do show unit and show bool. Okay. And you can also define product types which also behave as variant types. So in the following example, we are defining a pair type A and B, which is a pair of A and B. So how can we actually use this pair, right? I can say something like pair of 42 comma true, right? It's int and a bool. Let's clear the output and run it again, and hence we have the usage of a product type. Good. Moving along, let's continue. In the polymorphic variant types, we can combine recursion and polymorphism to define a binary tree. So let's try this example here. So we have a tree can either have a leaf node, or it can have a head and a left tree or a right tree. Let's just quickly check that we have not made any typos. I have made a typo. This extra semicolon should not be there, and then that's good, right? So that's a definition of a binary tree. So how do I actually use this, right? Let's say I want to, let me just say I want a head to be 1, and then I want to have say 2 and 3 as the left and right subtrees. So how do I define this kind of a tree, right? So I can do something like node of 1, this is the head, and then the left subtree will be again node of 2, it has 2 leaves, left and right, and then I have a node, head is 3, and this tree has leaf on left and right subtree, and then I close it, right? So that defines the tree that we want. Now we can define functions which operate on binary trees. So in the example here, two examples here, let's go through them. So we have a recursive definition of sum, which basically computes the sum of the head values. So if it is leaf, I just return 0, or for a node x, I'm just going to type it fully as left and right. I return a pattern match again. I just take x plus, and again I call the recursive function sum of left, and I call the recursive function on sum of right. Okay. So let's run this. So that looks good. Now I can apply this sum function in our example here, right? So how do I do that? I sum. I have to pass the tree here. So it's going to be node 1, node of 2, leaf and leaf, and node of 3, leaf and leaf, and of course it will be 1 plus 2 plus 3. We should get the result as 6, which is what we get here. Cool. We can also define a map function. Similarly, we have a map f. So I give me pattern match. If it is a leaf, I just return the leaf. If it's a node of x left and right, what I do is I call node, I apply the function to the head, and again I recursively call map with the function f to the left and map to the function right. Okay, let's clear the output, run this, and that's the definition of map. Now of course I can use this map definition in a tree. So for example, I can say map function, say it just multiplies the argument by itself. So I can pass a tree here, just 1, node of 2, leaf, leaf, and then node of 3, leaf, leaf. Okay. How do I have the right parentheses? 2, leaf, leaf, node of 3, leaf, leaf. Let's check that. I think I might be missing some parentheses here. Let's quickly check that. Function x, node of 1. Okay, you don't need the extra parentheses here. Yeah. Let's clear it again, and then we get the result of applying the function to the tree, and each head is multiplied by itself. So 1, 2, 3 becomes 1, 4 and 9. Okay, this is some functions pattern matching on the user defined tree. Of course we can have records. We have seen them briefly earlier. So let's continue by redefining the dungeon characters with records. Okay. Now in tuples we have seen the use of the first, second, and the third functions to extract the values, but in records we actually have a key value pair. Right? So I can define character as we have a name, which is a string, level, which is integer. Can have a race, which is a string, class type, which is a character class. We have alignment, firmness. These things we already defined earlier, right? So just reusing the definitions. Armor class as int. Let's quickly run this. Hopefully I have not made typos. Very good, that looks fine. And now we can actually define a new character, say Gorgor Bay. So we say let Gorgor Bay name is Gorgor Bay, and then we have level is 17, race is half ogre, we have class type as fighter, and alignment is chaotic, and R neutral, and then armor class is -8. Okay, let's quickly just run this character definition, and that looks fine. So now I can ask for specific attributes of Gorgor Bay dot say alignment, or Gorgor Bay dot class type, or Gorgor Bay dot level, right? And it should basically oops, I made a typo somewhere here. Let's check. This expressions type character is not a function, it cannot be applied. Gorgor Bay dot alignment dot class type, Gorgor Bay dot level. Let me check the definition. Name is fine, level is 17, race is a string, class type is fighter, alignment is chaotic, and R neutral, class -8, 10 to 17. Okay, I think we're missing the double semicolon. Yeah, let's try this again, and then that looks good. Okay, awesome. So this is using records. Of course, we can use the existing record, and say you want to only define a new Tograve using Gorgor Bay. Do you want to just change the name, right? So only with certain name changes, field changes, you can define name. I want to say level is 20, and then maybe the armor class is -6, right? So we can actually define a new Tograve character like this. Of course, you can do pattern matching and them as well. Type aliases are useful. So let's clear the output here, and so instead of just saying float and float, I can say latitude, longitude is float and float, right? And you can use this alias in your functions. So let's finish up with a final example. So this is a mathematical expression. So what we want to do here is for this expression n times x plus y, we want to symbolically output n times x plus n times y, right? So how can we combine whatever we have learned, recursion, user defined types, constructors of values, everything, right? And do the symbolic computation. So for that, we are going to define a type expression right? So it is either a plus of expression or it is a minus of expression, or it's going to be a multiplication operation, or it's going to be a division operation, or we have a string, right? Let's run that. That looks fine. We're going to actually define the expression that we want. So it's going to be E, which is n times x plus y. So we just call it as times of variable n and plus variable x and variable y. Okay, let's run that. That looks good. And then to output the result, we are going to define a two-string function. Okay, so let's define that here. So recursive function, we are going to use the function keyword, and for plus of E1, E2, I'm going to output open parenthesis and then concatenate it with toString of E1, and we have the plus symbol, and then toString of E2 and concatenate with the close parenthesis, right? So just for this example, I'm only going to change the constructor and the symbol. So I'm just going to copy paste just for this example here. This is going to be minus, and I'm going to change the symbol to minus. And then the next one is going to be multiplication, so it's going to be times, and I'm going to change this to asterisk. Okay, and then we're going to do for divide. I'm just going to replace this with forward slash. Okay, and finally for var b, I'm just going to return it. Let's check we have not made any mistakes here. That looks fine. And finally we can write the actual function. So again, a recursive function distribute for times, for if it's E1 times plus E2 and E3. Okay, I'm going to call plus times distribution of E1 and distribution of E2. This is the expansion that we want, right? So I basically only want this one, but for the sake of completion, we will write the rest of the definitions. E1, E2 and E3, and plus times of distrib E1 comma distrib E3 and times distrib E2 and distrib E3. It's done. And then we define for plus as E1, E2 plus distribute E1 and distribute E2, and then we just define for minus of E1, E2 as minus E1 distribute E2. Made a mistake here. Remove the extra s. and then we do times of E1 E2 as times of E1 and distribute E2, and then divide of distribute E1 distribute E2, and then the last case for var we just call it. Hopefully that looks good. Yes, no errors. And now we can actually call our function. So we can do E, our expression, we want to pass it to distribute function, and then we want to call the toString function, and we just want to print it out, right? And this should give us the output, which is what we want, n times x plus n times y. Okay, that's good. Now can we do the reverse, right? Can we do the factorization? So given n times x plus n times y, can I get the common sub expression out? Can I get n times x plus y? So that is implemented by this top factorize function. Let's try this. So plus times E1 and E2 and times E3 E4 when E1 is equal to E3 we do times of E1 plus, this is the taking out the common sub expression out, right? And in the case of plus times of E1 E2 times E3 E4 when E2 is equal to E4 we do times of plus E1 and E3 E4. For any other case we just return E. Let's check if this is good. Yeah, that looks fine. So we can actually now use this top factorize function, top factorize of plus, we do n and x, right, and plus times of nx, we have to call times of n and y. Close this, we have to close one more parenthesis, semicolon, we clear the output and we run it, and we get the result here, right, n times x plus y. So that concludes this section. So do try it out. Go through each of these code examples, read the documentation, open ocaml.org/play. Let me paste that in the channel as well, and then try these yourself, type it down so that you understand the syntax and the actual usage. So I will make this recording available again on my YouTube channel here. I have pushed the code examples and the short notes that I have used in preparing this on the Twitch repository. So let me paste these links as well in the chat so that you can watch the video and refer to the same. I did ask a poll regarding starting Emacs sessions. I did get some good feedback. So along with OCaml, I think we'll start with some Emacs tutorials and then we can go through the manuals as well. Alrighty, with that, let me stop the recording and let's see who's online, and we can rate the next streamer.